Hey guys, so let's talk about the rest of chapter 6. I originally had a separate video for this, but we didn't get as far as I wanted to in class. And so I added some examples to the slides. So these slides are a little different than the ones we had in class on Wednesday, but you can download them from Blackboard. And I tried to come up with some non-sports examples for this section. And what I did was I was listening to a current rebroadcast of a Freakonomics episode about grit. And I think that's a really interesting topic about resiliency. So we're going to use those examples today. So we ended here talking about standardizing scales and comparing between z-scores. So I just want to back up and cover some examples from the first couple of things we did on Wednesday. So let's say we are interested in the spelling bee, and we want to know if we have an unusual year where students are returning to the spelling bee, like they're coming back for round 2, so to speak, more often than normal. So we want to convert this to z. I also wanted to use this example to really show you that while z-scores, we're going to talk about percentile ranks and percentiles for z-scores, that's not the same thing as the scale being a percent. So I can have a scale be in a percent score or a Likert scale 1 to 7 or means from 0 to 100, and that has like literally nothing to do with z. So don't let that confuse you. So if they're talking about percentile rank or percentile, they're talking about something I'm going to get to a little bit later in this section. But if they just say percent, they're still talking about the raw scale. So here I really want you to get the distinction between raw scale scores, X, and Z scores. So let's convert this to Z. And you guys know I'm bad at math, so I'm going to make the computer do the math for me. And so to convert this set of scores to a Z score, we're going to take the 2014 returning spellers, so 24.8 minus the original amount, which is 20. Okay. So that's 4.8. Let's try to get this all on the same screen. It won't let me. And we're going to divide by 2.2, which is the standard deviation. So let's just open calculator here. Come on. Okay. So what I did to get this, to say clear, is I said, okay, 24.8 minus 20 is 4.8. I'm going to divide that by the standard deviation. It's 2.2. Okay. So 2.18. Okay. Now remember that standard deviations our z-scores are on a scale of standard deviations. That means that this year's number of returning sellers is 2 standard deviations above the mean. So that's twice standard deviations more than normal. And a number like 2 is really large. So once you do a little bit more of this z-score stuff, you'll see that 2 is an unusually large number. So let's say now I have the same kind of statistics, but what would a z-score of just 2 be? So this is an example of converting from z to x. Sorry, I had that backwards. So this one is converting x to z, and then this one is converting z back to x. So what I would do is take and use that other formula where I'm going to take a z-score of 2 times the standard deviation, 2.2, okay, and then add the original number, 20, the original mean, and so I'd have to have 24.4 for it to be a z-score of 2. Now we calculated the z-score for 24.8 to be 2.18, so it makes sense this is just a little bit lower. So my original score of 24.4% would be a z-score of 2, whereas 24.8% is a z-score of 2.18. Okay. So they're very close together. And I can do this with any statistic. What would a z-score of 0 be? Well, this is actually very easy because that means it's the mean, but we could fill in that formula. We could say 0 times the standard deviation. Okay, oops, I must have hit plus, sorry. So 0 times the standard deviation, 2.2, okay, 0, plus 20, okay, it's 20. So anytime they ask you about what the score for a z-score of 0 would be, it's the population mean. Okay. All right. So now let's say I want to compare the spelling bee to this a beauty pageant. And so we already know the z-score for the first one. Well, actually, I changed the numbers here a little bit, so let's recalculate. Okay, so for the spelling bee, I've got 24.8 minus 20 divided by 4 in this example. That's 1.2. So that was, first one's a z-score of 1.2. And now I want to compare that to this beauty pageant, but it's got totally different statistics. It's still in percentages, but it's different statistics. So let's take 23 minus 15 divided by 5. That's 1.6. So the first one is 1.2 and the second one is 1.6. So what that means is that the beauty pageant has more returning women than the spelling bee because their z-score is higher. So sort of who has the most returners, even though 24.8 is a bigger number than 23, the z-score, when I standardize the scales, it shows me that the beauty pageant has more people returning because they have a higher z-score. So you can use z-scores to compare when people are on different scales, like a 1 to 10 versus a 1 to 5, but you can also use it when they have different criteria for their scales, meaning they have different means and standard deviations. All right, so let's now get into this percentile issue. So z-scores tell me where a value is on a normal distribution, right? So z-scores that are positive are above the mean. Z-scores that are negative are below the mean. And because this is a distribution that we understand well mathematically, there are rules about how a z-score translates into a percentile. So we talked Wednesday, I said, I promise you we're going to get to how z and p, as in probability, relate to each other. And so we can calculate an area under the curve. Thankfully, that calculus has been done for us to translate to a percentile rank or a percent score. And so this is called the 34-14 rule, meaning that 34% of the scores fall between 0 and 1, 14% of the scores fall between 1 and 2, and then the last 2% to add up to 50% total on this whole side over here are from 2 to the end of the distribution. And so that's why I said when we get into this, you'll see that a score of 2 means that it's very high. Okay, so having a score of 2 here means you're in the top 2%. Now, we talked about this also being a hot dog fold. So the left side and the right side are the exact same numbers. So it being symmetric makes this very, very nice to calculate. So there's 34% between 0 and -1 standard deviation, or 1 z-score, 14% between 1 and -2, and 2% -2 and out. So this being equal on each side is really useful for us. And there are numbers, so a half here would be 17% approximately, so z-score of 0.5 is halfway in between here. But what we'll do is we'll use R to calculate these for us precisely. So this rule is just to help you kind of remember. It's really to help you judge what's going on, so always draw these normal curves. So you're going to get to see some really bad drawings of me with my trackpad on my Mac here. The book includes a table, a z-score table. Now, that is useful if you don't have computers. And what we have is we have a program that'll calculate this for us, so I don't even have to think about looking at this up in a table. But I do want to highlight here, red, this section here, and like I said, I can't draw on this very well. It says the negative statistics are not included because all we have to do is change the sign. So one of the questions that will pop up, quiz, homework, whatever, is that why are there no negative z-scores on a z-table? Or why do we not need the negatives on a table or in R? And that's really because they're exactly the same. The top half and the bottom half of a distribution are symmetric, like hot dog folds. So then the numbers over here from 0 to 1 are the same as the numbers from 0 to -1. So only the positive numbers are on the table because the distribution is normal and symmetric. So I want to argue that tables are dumb, and let's just get the program to calculate for us. Well, a little less likely to make mistakes. So one of the biggest suggestions is to always sketch this curve out, especially as you're first learning it. And for the same reasons that you needed to sketch out a skewed distribution, is to make sure you understood which side the tail was on. It allows you sort of a practical reference of thinking about what your score is going to be. And to me, it really allows me to make sure I'm doing this right in R. So the way you calculate this in R is, this is an important point here. We're talking about getting p-values or probabilities from a z-score. So make sure you understand that this particular code here, this p-norm thing, is all about getting p. I want p, and the code has p at the front. Okay, so p-norm gets you p. We're going to put in the z-score. So remember, the italics things here are what's changing. It's hard to tell since they're single letters. This isn't a column of data. It's literally one number. So I would type in z. Lower tail here. Lower tail means which side of the distribution do you want. So here's my bad normal distribution. Don't judge. Ooh, my not straight line at 0. This side is where lower tail is false, because it's the upper half of the distribution. This side is where lower tail is true, because it's the bottom half of the distribution. Okay. That's not 100% hard and fast, the rule, but anything where you want it on the right side of any line, do false. Anything where we want the left side, do true. So what does that mean? That means if I have a different normal distribution, I'm interested in this line up here where the z-score is way up here, this side is still false, this side is true. Okay. So the left and right side stays the same, but the line may move around. So when I say lower tail equals true, what I mean is I want the probability of all of this here on the left. If I say lower tail equals false, it means give me all the probability on the right. And you'll get an example here in a minute, and hopefully that'll be a little clearer which side you want. And then when we practice, we'll talk about this some more. Okay. So what I did for these examples is I took Angela Duckworth's grit scale. So this is in the Freakonomics episode, where she was talking about just like grittiness, hardiness. So there are some really great examples. Let's click on this. So you should go to this link, take the grit scale. So new ideas and projects sometimes distract me from previous ones. No, I got things I gotta finish. Setbacks don't discourage. Not the same word as discover. I don't give up easily. Yeah. So you can answer this at the very end. You'll get your score. That's my score here. So I averaged a 4.5. And they tell me when I do that I averaged higher than 90% of Americans in our study. So how the heck did they get this number? And that's what we're doing. So we're calculating the percentile rank, kind of like high school, your percentile ranks, by using z-scores. Okay. So my numbers that I'm about to give you an example for won't turn out to 90%, but this is how they might have gotten that sort of number. So if I want, and I ask you, this is example number 4, remember there's a list of 8 types of things that you should be able to do at the end of this section. Let's say I'm trying to calculate a percent above a z-score. So if someone makes a z-score of 0.98, how many people are above them? So what percent of scores are above them? So this is where you would say lower tail equals false, because remember you want everything on the right, and then lower tail equals true if you wanted everything on the left. Okay. So we should be able to calculate percentiles above and below positive z-scores. So one of the problems that people have when they're calculating these numbers from a table, so let me back up a slide here, is this is pretty easy, right? Because when I look at a table, it actually only shows me, so let's see if I can get the pen to work. It's being grumpy McGrump pants, so here. The table only shows me this 50%. What it implies is that there's another 50% over here on this side of 0. Okay. right? So the whole distribution has to add up to 100% because probability adds up to 100%. And if I ask you about the percent above, people can go, yeah, 16. But what happens when people look at tables is, oh, wrong way, they only look at this number when you ask them about below. And so they tell me it's 33%. And I go, it can't be 16 above and 33 below because that does not add up to 100. So this is why you should always draw it so that you can realize that this is 80% or 83%. The nice thing about using R is that you make that mistake less often. So let's try it. Let's say I made up these numbers, that the population mean for grit is 3. It's right in the middle. And the population standard deviation is 1.75 because we have a lot of really gritty people, then a lot of people who are not so gritty. And I made a 4.5 on this scale. So let's calculate the percent above my score and the percent below my score. So my score is above the mean, so I should get a positive z-score. So the first step in this process of getting percents is to calculate z. Write that down right now. Calculating percents involves having a z-score. So we're going to do that first. And we've done that already. So we'll do 4.5 minus 3. Okay, well, that mathematically did not turn out the way I expected. Let's try that. 4.5 minus 3. Okay, it's 1.5 divided by 1.75. And I got this 0.86. Okay, so my z-score is 0.86 above the mean. Let's load up Studio here. And so I could also do that in Studio. Let me make this a little bigger so I could do, now you will need parentheses here. If I can find the stupid parentheses button. That one. Yeah, so I get a 4.5 minus 3, right, divided by 1.75. And it gave me the same number down here. Oops, sorry, 0.86. Now the way this works is I'm going to use p-norm. And I'm going to fill in this number. So I can cut and paste it from the bottom, or 2 decimals. At minimum, 2 decimals. My lower tail, now do I want true or false? Well, let's think about this for a second. The question asked me for the percent above. Okay. Anytime I say the word above, lower tail is false, because I don't want the lower half, I want the above half. So we're going to do false here. Okay. So F for false. So there's 20%. Okay, now this is in proportion. So if you like this better in percent, you can multiply by 100. Okay. So it's about 19.57 or 20% of people whose scores are above mine. I am above the mean, right? My z-score is positive. But there's 20% of people who are still have higher scores than I do in this example. Okay. So what about the number of people below me? So this is above. Now to do below, we'll just type the same thing. p-norm, cut and paste our z-score. So notice this is not a thing of data. I have some data over here, but really when you load R, it's usually empty. So there's no data being pulled here. I just type the scores manually. Lower tail this time is true. How many people are below me? You guys, I can't type. It's been a long day. There we go. And I'm times that by 100. But before I do that, let's think about this for a second. If I said that right at 0.86, there's 20% of people above me, how many percent of people are below me? Remembering that this adds up to 100. Okay. And the answer should be about 80%. So this is just me thinking about the numbers I have to make sure I'm doing this right. Okay. And then I get a nice number here, 80%. So when you do above and below, those should add up to 100. And really what I've done here is I've taken my z-score. I calculated, so this is 0 here, z-score of 0. I'm here at 0.86, so this is me. So that means that there are 20% of people here and 80% of people here. That means that I am in the 80th percentile. So anytime I ask you for a percentile, what we're really asking for is this way. So how many people up to me is it? So I'm in the 80th percentile. So think about percentiles like your high school percentile. You want to be at the top. So it's how many people up to that point. But that actually means that its lower tail is true. I want to know how many people are behind me. The other way you can phrase this is that I am in the top 20%. So sort of two ways to think about that. When you talk about percentile, we're really trying to cover how many people are below me, right, and me. When I talk about top so many percent, I'm talking about how many people are above me, which is a little confusing. So just remember, percentile means everybody below. So I'm in 80th percentile, means there's 80% of people below me. When I say the top rank, I'm in the top 20% of people. Okay? Those tell me the same pieces of information. It's just which way you want to phrase it. Because saying you're in the 95th percentile is the same thing as saying you're in the top 5%. But it seems a little bit more like, ooh, when you say I'm in the top 5%, right? All right, so that's positive z-scores. What happens if I'm instead working with a negative number? And until I made the switch to R, this actually was the worst for students. Because the tables don't really include negative numbers, and people just found this very confusing. And I think if you can get over your little R kind of moments, this is actually a lot better. So when I calculate this sort of thing for R, one nice thing is this. Let's say I want to go this way. This is still lower tail equals false. Even though it's going to be, in this particular example, like 96%, it's still false because it's still the top end of the distribution. And then over here, this is lower tail equals true. So anytime you see the word calculate the percent above or calculate the top X percent, that's lower tail is false. Calculate the percent below, like this slide, is lower tail equals true. So let's say I redid this scale and took it again, and this time my sad face score when I was in a frustrated mood, I got a 2.5 instead. I still have to calculate Z first, so let's try this example. And let me draw kind of what's happening first. So we're gonna figure out where I am this time. Here's 0. I'm gonna be on the left side of 0 here. So let's try that. So my score is 2.5 minus 3 divided by 1.75 from a first example. Okay. Don't reverse the order of these just to make it positive. Z-scores can be negative. Z-scores are negative a lot. Remember in class we talked about that. It just means you're below the mean. So I have a negative 2.9 Z-score this time. So I'm going to take P-norm, and I'm going to calculate the percent above me, and I'm going to hang on to that negative. So when I double click in R, it looks like to me it doesn't hold on to the negative. So be sure that you copy the negative. And this time I do lower tail equals false, because I want to know how many people are above me. And let's stop and think about this for a second. So if I go back here and I say, okay, I'm here. So this is me again. On the negative 0.28. Okay, this is going to be terrible. Pretend. Remember that this side of 0 is 50%. So the number has to be greater than 50% because everybody who's above the mean is above me. So let's go back. And let's see what it is. So it should be a little over 50%. It's going to be more like 60%. Okay. So 61% of people who are above me. Now let's try that same thing again. Now, how many people are below me? Now for proportion of people below me, or percent of people below me, if the first time it's 61%, that means this should be 39%, because it still adds up to 100. Okay. So it's 38.75 if I work this out into decimals. Okay. So that's how you calculate lower and above and below, positive or negative z-scores. Remembering that anytime you ask for above, lower tail is false. It's sort of backwards. Anytime you ask for below, lower tail is true. So give me the bottom. So the way I remember this is lower meaning the bottom, Lower tail the bottom, yes for the left, no for the right. All right, so here comes now we can do some like interesting things with this. And this particular example is where we're going for chapter 7. So when someone tells you that something is statistically significant or p less than 0.05, what they're really saying is that they've calculated the probability of getting a score, a z-score in this particular example, on both ends. So the likelihood of getting this score on the positive or the negative end is less than 5%. Now remember, hypothesis testing is backwards. We want small probabilities because small probabilities imply that the likelihood of the null is very small. So remember, it's null hypothesis testing, we're testing the null. And we want the likelihood of the null to be small because that then therefore means our research is more likely to be true. And so what we do is we calculate the likelihood of getting our score if the null is true, the likelihood of being wrong if we are. And so here's a particular example where I try to scribble this out. And so if somebody asks you, what's the percent of people or scores between any two z-scores? So you can do this for any z-scores you like. So let's pick negative 0.34 and 1.02. And so what we're doing is this is a z distribution down here at the bottom. This is the whole distribution. So this first part here adds up to 100 here. And now let's calculate this number here. So what is the percent above negative 0.34? So we would say p norm negative 0.34. Lower tail equals false for the top. You guys, I cannot type. Let's try again. So don't feel bad when you type something wrong. I do it all the time. And it's 63.31%. So over here, this line is 63%. Now let's calculate the likelihood of 1.02 and up. You'll see where this is going in a second. So I'm going to do p norm 1.02 lower tail equals false times 100, and that's 15%. If I subtract these two from each other, I will get the distance between these two. So it's much easier to calculate the entire distance from 34 and up, or 0.34 and up, and the distance from 1.02 and up, and then just subtract. So let's do this. And that tells me that there is 48% of people between negative 0.34 and 1.02. And that's useful in understanding like how many percent of people are between two numbers. So they might ask you the percent between 1 and negative 1, which is 68%, or close to those numbers because of the 34-14 rule. Or we might ask like the extreme values. Now let's say we just did these backwards. So I'm going to rearrange here for a second. And you get a negative number. Okay, so if I do it this way, I get negative 0.47. Don't write that. Percentages are not negative. Okay? So percentages are not negative numbers. Here you would just leave off the negative. Okay? So let me go all the way back here. Now, why did I do the top? Why didn't I do the bottom? So let's say I do p norm negative 0.34. Lower tail equals true this time, times 100, minus p norm 1.02, lower tail equals true, times 100. Check that out. So the distribution is symmetric, meaning that it's the same no matter which way we go. And so as long as you are subtracting and you keep it as false, and then true and true, you'll be fine. So it doesn't matter if you go up or down here, but don't mix and match. Only go up or only go down. So let's calculate the percent between my two grit scores. And then let's calculate the percent outside my grit scores. So for this first one, what we're going to do is calculate the percent. Oh my goodness, you guys, it looks like a whale. The percent in the middle here. But then what if I want to calculate the percent on the top and the bottom? Okay, so the second one's a little harder. So let's do the first one. Okay. So I had originally calculated my two z-scores as this p-norm. Okay. And we're going to do the percent in the middle, so I'm just going to subtract these two bad boys. So all I've done is taken my original p-norm score here. I can hit enter here with the minus at the end, and that'll just stack the code for me. But I want to know how many people are between my two z-scores. And remember, it doesn't matter if it's lower tail is true or lower tail is false as long as they're the same. Okay. And this is for percent between scores. It's negative because of the way I subtracted, but it's about 42%. So there are 42% of people between a z-score of negative 0.29 and a z-score of 0.86. So if I, that means 42% of people fell between my two scores. Let's do the slightly harder one. So let's think about this. I want to know how many people are above my upper score and below my lower score. So I made a really bad car here. So I'm going to take my upper score and add it to my lower score. So this one's a little harder. So I'm going to do p-norm of my upper score. Goodness. So that's this crazy number here. And you can round this to 0.86. You'll get the numbers approximately. No, I'm kidding. So the score is above my upper score. Remember, it's above, so I'm going to use false. Times 100. I'm going to actually add that to my p-norm of my lower scores. Okay. Now, anything below my lower score is actually true. So I'm actually mixing and matching here. So this first one, they're the same when we do between, but when we do outside, you add. And you add and you switch sides here. Okay. But let's think about this. If there are 42 people between, so 42% of people here, well, this whole thing has to add up to 100. So we should get 58% of people who are on the outsides of me. Okay. And I hope we do, because I have not tested this. Okay. So we got 58%. So between my two scores, there's 42% of people. Outside of my scores, a more extreme, more away from zero than me, is 58%. And this first example is more like what will be on the test because it's a little easier. This second example is really more what we're going to do in chapter 7. All right. So let's go the other way. Let's this time get a z-score from a p-value. And so the important part here, the part that's different, is we're looking for z. We're not looking for percentile or proportion. We're trying to go back to z and look at the letter here. It's q. Okay. I don't know why it's q, but it is. It's q for everything that we're going to do for the rest of the semester. So p norm gives me p values, but q norm gives me z scores. Okay. And that depends on what option we want. Generally, let's talk about leaving it as lower tail equals. Ooh, that depends. So I'll do an example of both here. Okay. So we don't want to do that yet. Let's say I want to calculate what is the z-score for someone who, on this grit scale, what's the z-score for someone who's in the top 2%. Okay. So what kind of z do I have to be in the top 2? So we're going to do q norm. Okay. We're going to do 0.02. So this number here needs to be in proportion. You can't do percentages. So if you just did 2, it's going to freak out. Okay. So we'll just right now say lower tail is false. I'll tell you why in a second, and let's just run that, and it goes, blah! I can't do that. Okay. So we're going to say 0.02. And if I say we're in the top 2%, what that means, and here I'll draw this. If I'm in the top 2%, I wish there was a hard and fast rule for this, but there's not. So top 2%, my bad drawings, means I want everybody who's up here. And so I want to use lower tail equals false because I'm looking at for the people at the top. If I instead said I want to know the 98th percentile, I want to know here where there's 98% of people here. So remember that this would be lower tail equals true. So this one's true, this one's false. So it really depends on the wording of the question. So 0.02 here, lower tail equals false. My z-score is 2.05. Remember the 34-14 2% rule, so it's right around 2. Now if I'd asked that same question as the top 98%, I would say lower tail equals true, and I should get the exact same score. So these are opposites of each other. If I'm in the top 2%, I would do lower tail equals false. If I said I want to know what the 98th percentile is, meaning there's 98% of people below me, that's lower tail equals true. So that one's a little tricky in like which way should we go. I would say generally the questions end up being the top X percent. That's going to be lower tail equals false. And then the very last sort of thing that we're going to do is going from percentile to Z to X. So this is the most complicated one we're going to do. So the first time, let's say you say, what is the score someone has to make to be in the top 2%? So this is a very relevant question. So let's say you're taking the MCAT or the GRE or the LSAT or any of these silly standardized tests. And you are looking at a school that's really good and they say, we only take the top 5% of people. You're like, damn, I gotta get what score on the GRE to be in the top 5%. So this is a question that happens a lot. And so what we have to do is take percent to Z, because percent and Z are numbers that we understand together, and then go from Z to raw score. So you can't go from percent to X. You have to go percent to Z to X. And then we have to go X to Z to percent. So Z is the middleman, if you will. And so I wrote out an example here for the GRE at one point. And so I said, well, if the mean GRE score is 150 and the standard deviation, sigma here, is 5, and I want to be in the top 5%, what do I do? Okay. So if I'm in the top 5% Q norm, right, that's the second one here, it gives me a z-score of 1.64, or that means I'm in the 95th percentile. Okay, so these two are equivalent. That's what we just did with 2% and 98%. It's 1.64. And then I use that formula to convert back. So I said 1.64 times 5 plus 150. So on the GRE, to be in the top 5%, I needed to score 158.2. That's not really what the rules are, but that was just an example of how I could calculate the exact score I needed. So we'll go back to that grit scale. So what is the score, the z-score for the bottom 2%? So what score do we have to make on this to be in the bottom 2? So let's first convert to z. So now we're going to use Q norm to convert to a z-score. The bottom 2%, 0.02. Lower tail this time, I want the bottom. So the lower tail is true this time. Because I want to know the very bottom of the score and people below that. So it's a little weird to say in the top 98th percent. So this would be the second percentile, the people at the very, very end. And so this is a negative 2.05, and so I did this on purpose because remember that these two things are symmetric. So all you do when you change F to T is changing the negative sign. So that's the bottom 2%. Now I want to multiply that times the standard deviation. So remember the rule is z times standard deviation plus mu, which is 3. Okay. And hopefully this isn't negative. It's probably negative because I'm not good at examples, but this is how you do the example. So someone would actually have to score a negative 0.59, which means the scale is kind of bad because the scale only runs from 1 to 5. So you actually cannot score in the bottom 2% with my particular example, but that's how you would calculate it. You would take your z-score, so this is z, which we calculated as negative 2.05, multiply by standard deviation, add the population mean. So the answer to this first question, which is example 7 in our example sheet, is negative 2.05. The second question would be a negative 0.59. So I'm converting from percent to z to x. Okay. So we're going to end this section by talking about a distribution of scores versus a distribution of means. And this really plays nicely into chapter 7. So we'll come back to this idea a little more. But let's say we take a distribution of scores. Okay. So this is the population of scores. So each one of these little squares is a person. So each one of these little squares is a person. You know, some of us are hanging out over here. We got one outlier over here on the low end. Okay. But let's say instead we want to create a distribution of means. Check this out. This is the important word over here, means. So what happens? How do we create a distribution of means? We take these scores, we calculate the average. We take another sample of scores, we calculate the average. Another one, calculate the average. So here, each one of these little boxes is a person. Okay, so this one, it might be, you know, person 1, person 2, person 3. Here, each one of these little boxes is a mean. So it's a sample mean. So each sample here is averaged. So the difference between this is like kind of a theoretical point of like each sample is only one group of people, but the distribution of means here is a bunch of samples with a bunch of people. And it's a distribution of the average scores, or M, right, for sample means. And this is where we're going to come back to the central limit theorem. So we talked last time about how the more participants we add to a study, the more normal it gets. And that's also sometimes called the magic of large samples, or the mathematical magic of large samples, or the rule of large samples, the rule of large numbers, whatever. It's the central limit theorem. And we could have a distribution that is skewed. So this population distribution is skewed towards the bottom. We just have a couple of outliers at the top. So think about income. As we take a distribution of means, so this says it's only 2 samples. The important number here is 2. See how it's less skewed? So it's moved this way slightly. And as we add more samples, this is not more people, this is more samples. Look how normal this one is. It's like happy face, normal distribution time. Okay. And what that implies is that when we talked about samples, we said the more people you add, the more normal it is. Same rule applies to means. The more means you add, the more normal it is. And that is a very useful thing to have happen. And we'll talk about this more next week. Okay. So if you don't really get that concept with the way I just described it, this video is like the best thing since sliced bread. And I can't show a video in a video because it freaks out my computer. But you should click on the link and go watch it. It's just a couple minutes long. It's called Distribution Bunnies. And so it's a video that shows you the central limit theorem in action. And so it'll talk about this idea a little bit more. I think it's much cuter than I can possibly ever be because it's got little bunnies and dragons drawn out in cartoons on it. Okay, so go watch that. And just sort of end of like the central limit theorem is super important for statistics. So it's one of these math rules that just really makes statistics useful and worthwhile. Because without this, I don't think we would have as easy of a time calculating numbers that we know. Like the normal distribution would not be a thing. We wouldn't understand these percentages. So all those examples we just did would be a moot point. So the summary of CLT is a distribution of sample means and a distribution of people is normally distributed even when the population is not given enough people or samples. Okay? So as we add more samples and more people, it gets more normal. So the rule is the same, but so more people equals more normal. More samples equals more normal. Okay. It also means that the distribution of means is less variable. It is squished. It's kurtotic, right? So we're coming back to kurtosis. All that stuff you learned in the first test is still relevant. And so kurtosis implies like the spread of the distribution. So the distribution of means has a smaller standard deviation than a distribution of people. So the way I remember this is that people are weird and they vary a lot, but samples, not as weird. The influence of each one person is less. And so you got to think about this as states. Within states, people are weird. There's a lot of variance. But when you start to average states and pull together their overall statistics, there's less variance to be had because you've conglomerated them into one sample of people. Okay. And then the book chapter talks about how this is based on making beer better. So lots of statistics, early statistics were calculated because they were trying to calculate hop samples or wheat samples for beer. And so that also makes statistics really awesome, is that a lot of the things that we know about mathematical number rules are because people were trying to like get drunk. So I find that very amusing. And since you've made it with me this far, there's your funny story for the day. So let's talk a little bit about the distribution means, and then I swear I'll bug off. So the mean of the distribution tends to be the mean of the populations. So what the heck this means is that the mean of a population, remember, is mu, that weird little u thing. That is equal to the mean of a distribution of means. So you'll see this listed as mu and then an m next to it. It's on the next slide too. Okay. However, the standard deviation of a distribution of people, so sigma, is less than the standard deviation of the population. Okay. So what we're going to calculate here is standard error. This is important. So when you see sigma m here, what it means is standard error, and it means it's calculated on a distribution of means. So this little m is very important. It tells me that I am calculating my numbers on a distribution of means and not people. Okay. And the formula for that is sigma, standard deviation, divided by the square root of n. So the way I explain this to my upper level class is that it's Oprah. It's the Oprah of standard deviation. So it's called standard error. And I call this the Oprah because it's like you get some and you get some and you get some. Okay, from Oprah's days of you get a car and you get a car and you get a car. And what happens is we sort of take the sample size here and figure out how many people there are. And so this is why it gets squishy. So the larger the sample size here, the more squishy it gets. So it shrinks up because the more people we have, the more precise our measurement is. So the standard error gets smaller. Okay, both standard deviation and standard error get smaller, but standard error gets a lot smaller. Okay. We're going to cover this topic a whole lot more in Chapter 7 because it's important for the hypothesis testing part of Chapter 7. So if you're kind of like, I don't know if I totally get this, we're going to do this some more. Okay. So to kind of give you this pictorially, this orange line here is the distribution of scores. That's the peopleness. Right? And so you see the spread is kind of far. And that's the original graph, the height graph from here. And so it's kind of flat. It's platykurtic. But when we take a distribution of means, look, it's so pretty. It's normal. It's squished up a little bit. So the standard deviation of this distribution of means, which we're calling standard error. So this one is standard error. Okay. So we're listing that as sigma m, is much smaller this way, right, than the distribution, the standard deviation of the distribution of scores. And so that's really what I want you to get, is that in a distribution of scores, each individual person has a lot more pull to the tails. But in a distribution of means, it kind of like takes all those tails and averages them together and squishes the whole thing up. Okay. It also gets more normal. All right, and then just kind of to end all of this, there's a symbols chart. So if it's scores, it's mu and sigma, and it's called standard deviation. If it's a distribution of means, a whole bunch of different scores averaged together over and over again, it's got the little m's on it. So that's how you know it's a distribution of means, is it's got this nice fat label of an m, and it's called standard error. So the Z statistic for distribution of means is the same damn formula. So don't get freaked out by the symbols, but it's approximately the same formula, right? So x minus mu divided by sigma. And the big difference here is this. So it's mean minus mu, so mean minus mean, over sigma. But remember, we got to calculate this thing. So sigma m, right, equals sigma over the square root, oh, I was doing good, of n. Okay. And why is that? Well, for a distribution of scores, we have one person. We're only interested in one person. So the square root of n is 1. Right? Here we have multiple people. So this is a sample of people. So we got to deal with the peopleness of it and divide by the square root of n. Okay. And like I said, we're going to cover this a lot more next week. So if you're a little shaky on it, listen to me next week and then ask lots of questions. But for that, let's go back to, and this is the very last slide, cheating. So we started this lecture by talking about patterns of cheating from Freakonomics. How the hell did they figure that out? Right? He talks about how the patterns became obvious because they can't really actually tell you how they figured this out. But what they did was they found that they took the probability of these likelihoods. Okay. So here's Z out here. And they said, how likely is this pattern of scores to happen this many times? And so that kind of goes back to the gambler's fallacy of if something hasn't happened in a long time, it's bound to happen. In reverse. So they said, okay, here's this pattern of scores, A, B, C, D, A, B, C, D. How likely is that to have happened that many times? And they calculated the Z statistic for it. And what they found was that it's very unlikely for that to happen that many times in a row. Okay. And this then goes back to reproducibility. So there's this pressure for researchers to cheat, to get published, to keep our jobs. And so we can calculate how much people are cheating by looking at the likelihood of their scores that they get. And when you have lots and lots of numbers here at the very top, these very high Z scores in the 6 and 7 range, this is totally probability-wise unlikely. It's probably because somewhere someone's cheating because it's more publishable if it's past this red point here. So the fact that there are so many scores here at the top implies that something nefarious is going on. And so people are likely to cheat. Okay. So we started and ended with cheating, but go and make sure you can do all of these Z-score examples, and then we will talk about those more on Monday and take a quiz.